Hello there, and welcome to the Sleepy Science Channel. Tonight, we are drifting into the quiet, magical, and surprisingly powerful world of crystals. These are not just pretty stones or sparkling decorations. They are shapes born from patience, pressure, and time. They form slowly, atom by atom, guided by rules so precise they can shape mountains, store memories, and keep the rhythm of our modern lives ticking along. Crystals connect the deep interior of the Earth with the smallest technologies in our pockets, linking geology, light, electricity, and even life itself. As we explore this world together, you may begin to notice how often crystals quietly support the world around you, holding structure, shaping energy, and preserving stories far older than humanity. There is something soothing about their appearance, something calming in their presence, and something humbling in how much complexity can arise from simple patterns, repeated gently over time. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is relax. Let your shoulders sink, your breathing slow, and your thoughts soften at the edges. Allow your eyes to grow heavy as your mind unwinds, and together, we wander into this quietly fascinating world. Let's begin. Crystals grow by stacking atoms into repeating patterns, like nature's own code. In a crystal, atoms do not gather randomly. They choose a rhythm. Picture a tiny building block, so small you could never see it, repeating again and again in all directions. That repeating block is what gives a crystal its predictability, its flat faces, and its sharp angles. It is also why one crystal can break in tidy ways, while another splinters. This hidden order is called a lattice, and it is like a set of rules that the material follows while it grows. Change the rules, and you change everything, including how the crystal bends light, carries heat, or responds to pressure. Even when a crystal looks rough on the outside, inside it can be astonishingly organized, with patterns that hold steady over immense spans of time. Your table salt is a crystal, built from perfectly arranged sodium and chlorine. The next time you sprinkle salt onto a meal, you are scattering countless tiny cubes. That cube shape is not a coincidence, and it is not the work of a careful machine. It comes straight from the way sodium and chlorine lock together, repeating their positions in a strict three-dimensional grid. Under a microscope, many grains of salt look like little blocks, chipped and worn from travel, yet still following that underlying geometry. This structure helps explain why salt cracks in certain ways, and why it dissolves so smoothly in water as those orderly ions pull apart and drift away. Long before modern chemistry, people valued salt so highly, it shaped trade routes and taxes. It is a humble kitchen mineral, yes, but it is also a daily reminder that crystals are not rare wonders. They are everywhere, hiding in plain sight. Snowflakes are ice crystals, each shaped by temperature, humidity, and timing. A snowflake begins as a tiny seed, often a speck of dust or pollen, floating in cold air. Water vapor gathers onto that seed, and the moment it freezes, the crystal stops following the rules of ice, building a six-sided symmetry. From there, the shape becomes a diary of its journey through the clouds. A slightly warmer layer encourages plates. A colder, drier stretch favors slender needles. A humid pocket can make branching arms that race outward like delicate ferns. This is why two snowflakes can share the same basic symmetry, yet still look different in their details. They have lived different lives in the sky. And because the growth happens so quickly and so sensitively, tiny changes in the atmosphere can leave visible signatures, like weather written in lace. Quartz can turn pressure into electricity, a trick called piezoelectricity. If you squeeze certain materials, they do something unexpected. Instead of only resisting the force, their internal charges shift, and a small electrical voltage appears. Quartz is one of the most famous examples, and this effect is not magic. It is geometry. In quartz, the atoms sit in a pattern that does not perfectly balance when pushed, so pressure nudges positive and negative charges slightly apart. That separation becomes usable electricity. Press in a rhythm, and the crystal responds in a rhythm too, converting motion into a measurable signal. This is why quartz shows up inside sensors that listen for vibration, detect pressure changes, or track tiny movements with remarkable reliability. The astonishing part is how consistent the response can be. A crystal grown by slow geological processes can behave like a precision instrument, simply because its internal arrangement is so faithfully repeated. Nearly every digital clock keeps time using a vibrating quartz crystal. Deep inside many clocks and watches sits a tiny sliver of quartz that hums at a steady pace when given an electric push. Engineers often shape it like a tuning fork so it vibrates cleanly, and they commonly choose a frequency of 32,768 vibrations per second because it can be neatly divided down into 1-second pulses. What makes this so soothing to imagine is that timekeeping becomes a kind of listening. The clock is not counting minutes the way we do. It is counting an orderly tremble in a crystal, over and over, like a quiet heartbeat made from stone. Temperature and manufacturing details still matter, so devices are designed to keep that vibration stable. And yet the core idea remains wonderfully simple. A natural mineral grown by the earth can be persuaded to sing a dependable note that guides daily life. Diamonds are crystals of carbon, forged under crushing heat deep underground. A diamond begins far below the surface, where carbon atoms are forced into a tight, orderly arrangement under extreme pressure and high temperature. For many diamonds, that starting point is deep in Earth's mantle, far beyond any mine a person could dig. The journey upward is dramatic. Rare volcanic eruptions can tear through the mantle and carry diamonds toward the surface inside fast-moving pipes of rock. Without that rapid ride, diamonds would not survive the trip in their stable form. When miners find them, they are not discovering something that formed near the ground. They are holding a messenger from a depth most humans will never experience, a crystal that can be billions of years old. Some diamonds even carry tiny trapped minerals, and those inclusions act like clues, hinting at the conditions of an ancient hidden world far beneath our feet. Rubies and sapphires are the same crystal, colored by tiny impurities. It surprises many people to learn that ruby and sapphire are not separate minerals. They are both corundum, a crystal made mainly of aluminum and oxygen. The difference is in the trace guests that slip into the structure while it grows. A little chromium can shift the way the crystal absorbs light, and the result is the deep red we call ruby. Other trace elements can produce blues, yellows, greens, and even pinks, creating sapphires of many shades. So two stones can show the same inner architecture, yet look like completely different treasures. This is one reason gemstones feel so story-rich. Their color is not paint on the outside. It is information inside the lattice, a chemical whisper captured during formation. Even the most famous jewel tones can come from impurities so small they would be measured in tiny fractions. A crystal's internal defects can create vivid colors without any dye. Perfection is not always the goal in nature. Sometimes a missing atom, a shifted layer, or a tiny pocket of trapped charge can change everything about how a crystal looks. These imperfections are called defects, and they can create what scientists often describe as color centers. Instead of an added element doing the coloring, the crystal's own structure alters which wavelengths of light get absorbed. Smoky quartz, for example, can darken when natural radiation rearranges electrons within the lattice. In other minerals, a vacancy where an atom should be can hold an electron like a tiny prisoner, and that subtle change can tint the whole stone. What is remarkable is the scale. A crystal can be mostly orderly, yet a scattered population of defects can paint it with blues, purples, or browns. The color becomes a record of stresses and exposures, a visual trace of its long, complicated life. Some crystals split one beam of light into two, creating double images. There is a famous demonstration where you place a clear crystal over printed text, and suddenly the letters appear doubled. That is birefringence. And it happens because the crystal does not treat light the same in every direction. Inside, the structure guides different polarizations of light along slightly different paths, so one incoming beam becomes two outgoing beams. Calcite is a classic example, once prized as Iceland's spar, because it can make this effect strikingly obvious. Beyond being a delightful surprise, birefringence is useful. It helps scientists study stress in plastics and minerals, and it plays a role in optical tools that control polarization. It is also a gentle reminder that light is not just brightness. It has direction and structure, and certain crystals are built in a way that reveals that hidden complexity with a simple, almost magical-looking split. Many modern lasers depend on carefully grown crystals to amplify light. A laser is not just a bright beam. It is a carefully disciplined one, where light waves line up and move together. To make that happen, many systems rely on solid crystals as the active material, chosen for how they handle energy and light. In one common approach, a crystal host is doped with special ions, such as neodymium, that can store energy briefly and then release it as photons. Mirrors bounce those photons back and forth, and the crystal amplifies them into an intense, coherent beam. Other crystals act as helpers, shifting the color of the laser light through processes like frequency doubling, turning invisible infrared into bright green. The crystal must be grown with extraordinary care because tiny flaws can scatter light and waste energy. So behind a clean, steady beam is a quiet triumph of materials science, where order at the atomic level becomes precision you can see. Crystals can form from cooling magma, freezing rock into mineral order. When molten rock begins to cool, it does not turn solid all at once. Different minerals start to appear at different temperatures, like a slow parade of new textures emerging from a glowing melt. Deep underground, where cooling can take thousands or millions of years, crystals may have time to grow large and well-shaped. In some granites, you can see individual mineral grains with the naked eye because the melt cooled gently, giving atoms time to settle into place. In fast-cooling lava at the surface, the same ingredients can freeze so quickly that crystals stay tiny, or the rock becomes volcanic glass with almost no ordered structure at all. This is why two rocks born from similar magma can look completely different. Their crystals are a record of cooling speed, chemistry, and the hidden journey of heat escaping into surrounding stone. Others crystallize from evaporating seawater, leaving minerals behind like fingerprints. Imagine a shallow lagoon cut off from the open ocean where sun and wind quietly steal water day after day. As the water level drops, dissolved ions become more and more crowded, until the solution can no longer hold them. Minerals begin to fall out in a predictable sequence, forming what geologists call evaporites. First one mineral becomes saturated, then another, and each layer tells you how salty the water became and how the climate behaved. In places like salt flats, you can sometimes watch fresh crusts appear after a hot stretch as crystals push upward from brines beneath the surface. Over long periods, these deposits can become thick underground beds that later feed mines, salt domes, and even natural traps for oil and gas. The crystals are not just leftovers. They are a chemical diary of ancient coastlines, dry seasons, and vanished seas. Metamorphic crystals grow when rocks are squeezed and heated for ages. Some crystals are not born from melting or drying. They are rebuilt while still solid, inside rock that is being slowly reshaped by the planet's movement. When buried layers are heated, pressurized, and stretched, the minerals inside can become unstable and rearrange into new forms. The result is metamorphism, a kind of deep earth renovation. A muddy rock can transform into slate, then schist, then gneiss, each step reflecting growing heat and pressure. Crystals may align as they grow, creating the silky sheen of mica-rich rocks or the banded look of gneiss that resembles frozen wood grain. This is not a quick process. It can take millions of years of tectonic pushing, folding, and burial. Metamorphic crystals are proof that even solid stone can change its mind, reorganizing its atoms without ever becoming liquid. Crystals can also grow from hot groundwater, filling cracks like slow cement. Rock is rarely as solid as it seems. Tiny fractures and open spaces can carry hot water rich with dissolved minerals, especially near volcanic regions or deep fault zones. As that water moves and cools, or as pressure changes, minerals can suddenly become less soluble and begin to deposit on the walls of those cracks. Over time, the empty space narrows as crystals grow inward from both sides, sometimes meeting in the middle like a carefully sealed zipper. These mineral-filled cracks are called veins, and they can form spectacular crystals of quartz, calcite, or other minerals, often with striking shapes because the crystals had room to grow into open space. Veins can also concentrate valuable materials, including gold, which may precipitate from the fluid under just the right conditions. It is a quiet kind of construction, where water becomes a mason and crystals become the mortar. Geodes begin as hollow spaces, then line themselves with sparkling crystals. A geode starts with an emptiness, which is already a little surprising. The hollow can form inside volcanic rock when gas bubbles are trapped and the lava hardens around them, or inside sedimentary rocks where nodules develop and leave a cavity behind. Then comes the slow decoration. Mineral-rich water seeps into the space again and again, and each visit leaves behind the thinnest coating of crystal material. Layer by layer, the interior changes from rough stone to a glittering chamber. Sometimes the first lining is a smooth band of microcrystals, and later growth produces larger points that reach inward like a quiet, sparkling forest. The outside can look ordinary, even dull, which makes the reveal so satisfying. Breaking one open feels like discovering a secret room. And in a sense, it is. A geode is a geological surprise that took patient repetition to build, hidden in plain sight, until the moment it finally opens. Amethyst gets its purple from iron and natural radiation inside quartz. The deep purple of amethyst is not painted on. It arises from trace iron inside the quartz structure, paired with a subtle nudge from natural radiation in the surrounding rocks. Over long periods, that radiation can shift electrons into new positions, creating a change in how the crystal absorbs light. The result is a purple tone that can range from pale lilac to intense violet, sometimes with bands that mark changes during growth. Amethyst often forms in cavities where quartz has space to build points, which is why it is so common to see it lining geodes and volcanic pockets. Historically, it has been prized for jewelry and carved objects. and it has traveled through myths and royal collections for centuries. But even without the stories, the science is lovely. A nearly invisible ingredient and a quiet background energy can, over time, coax a clear mineral into a color that looks almost unreal, yet is completely natural. Citrine is usually quartz too, colored by heat and trace chemistry. Citrine carries the warm look of sunlight, but its story often begins in the same family as amethyst. In many cases, the yellow to orange tones come from how heat changes iron-related features inside quartz, shifting the way the crystal interacts with light. Nature can provide that heat through slow geological warming, nearby intrusions of hotter rock, or changes in burial depth over time. This is why citrine is frequently associated with environments where quartz has experienced a different thermal history than its purple relatives. The color can be delicate and champagne-like, or deeper and honey-rich, depending on conditions. It is also a reminder that gemstones are not only about what is present, but about what happened. Temperature is a powerful sculptor at the atomic scale. It can rearrange tiny charge patterns and transform a crystal's appearance without changing the basic mineral at all. One quartz can whisper cool violet, another can glow golden, simply because of heat. Emerald's green comes from chromium or vanadium inside the beryl crystal. Emerald is beryl, a crystal built from beryllium, aluminum, silicon, and oxygen, arranged into a sturdy framework with channels running through it. The famous green arrives when chromium or vanadium slips into the structure in small amounts, shifting how the crystal absorbs and transmits light. What makes emeralds especially intriguing is that the geological recipe is demanding. Beryl often forms in one kind of environment, while chromium-rich rocks often come from another, so emeralds tend to appear where unusual geological circumstances bring those ingredients together. That can mean complex boundaries between rock types, or fluids that travel and mix in just the right way. Many emeralds contain internal features called jardins, a garden-like tangle of inclusions, which can reveal how they formed and can make each stone feel uniquely alive. Instead of perfection, emerald often offers character, with green that seems to hold depth like a forest seen through clear water. Aquamarine is beryl as well, tinted blue by iron in the lattice. Aquamarine shares its mineral identity with emerald, yet it tells a different color story. Here, iron takes the starring role, and its presence in the crystal structure influences which wavelengths of light are absorbed, leaving a blue to blue-green clarity that can resemble seawater. Aquamarine crystals often grow as long hexagonal prisms, and some can become impressively large, making them favorites for collectors and for jewelers who want big, clean facets. The color is sometimes stronger in particular directions within the crystal, so cutters pay attention to orientation, turning the rough stone to find the most pleasing face. In the natural world, aquamarine can form in granitic pegmatites, where the last fluids from cooling magma are enriched in unusual elements and allow big crystals to grow. There is something calming about its origin story. It is not a crystal born from chaos, but from a late, lingering stage of geological cooling, where the earth gives a mineral room to become clear, spacious, and serene. Garnet is a whole mineral family, not one gem, with many chemistries. When people say garnet, they often picture a deep red gem, but the name actually covers a family of related minerals that share a similar crystal structure while swapping different elements in and out. That chemical flexibility means garnets can appear in many colors, including green, orange, and even near black, each variety reflecting a different mix of ingredients. Some form in metamorphic rocks, where they grow as new minerals during heat and pressure, and their size can hint at how long conditions stayed steady. Others appear in igneous settings. Garnets are also used beyond jewelry. Certain types are hard and sharp enough to be crushed into abrasives for sandpaper and water jet cutting, where they help shape metal and stone with focused force. The family nature of garnet makes it a perfect example of how crystals can keep one basic architectural plan while inviting different atoms to move in. One structure, many personalities, and a surprising range of uses. The same mineral can crystallize in different shapes depending on conditions. A mineral's name can stay the same while its outward shape changes dramatically, and the reason is almost like choreography. The inside follows fixed atomic rules, but the outside depends on the environment it grows in. If a crystal has plenty of room and a steady supply of building material, it can develop crisp faces and classic geometry. If it grows crowded among neighbors, it may become stubby, tangled, or oddly shaped, even though its internal order is the same. Changes in temperature, how quickly material arrives, and even tiny shifts in chemistry can favor one set of faces over another, like choosing which sides get to show. This is why a museum crystal can look like a perfect textbook diagram, while the same mineral in a roadside rock looks like a rough grain. The shape is not only what it is, but how it lived while it was forming. One substance can have multiple crystal forms, called polymorphs, with different properties. Sometimes nature plays a dazzling trick. The same exact chemical ingredients can arrange themselves into different crystal structures, and those structures can behave like different materials. This is polymorphism, and it matters more than most people realize. A polymorph might be harder or softer, denser or lighter, more stable or more likely to change over time. It is like taking the same set of building blocks and snapping them together into different architectures, each with its own strengths and weaknesses. This idea shows up in geology, where pressure and temperature can push a substance into a new arrangement. It also shows up in everyday products, where a material's crystal form can affect how it dissolves, how it reflects light, or how it holds together. Polymorphs remind us that matter is not only about chemistry. It is also about arrangement, and arrangement can change the story completely. Carbon makes both graphite and diamond, depending on crystal structure. Carbon is a master of disguise, and it proves it with two famous forms that could not feel more different. In graphite, carbon atoms link into wide, flat sheets that slide over one another easily. That gentle sliding is why graphite can leave marks on paper and feels soft to the touch. In diamond, those same atoms lock into a rigid three-dimensional network, like a perfectly braced scaffold, and the result is extraordinary hardness. The difference is not the ingredient, but the architecture. The same element, rearranged, becomes either a dark, slippery mineral or a clear gemstone that can survive rough conditions. This is one of the clearest lessons crystals can teach. Structure is destiny, and it also makes carbon feel almost alive in its versatility, as if it can choose a personality based on the pressures and temperatures of its birth. Calcium carbonate becomes calcite or aragonite, changing how seashells are built. Many seashells and marine skeletons are made from calcium carbonate, but the ocean gives that material more than one way to organize itself. Calcite and aragonite share the same chemical recipe, yet their crystal structures differ, which changes how they grow and how they respond to their environment. Some organisms build with one form, some with the other, and some even switch depending on life stage or conditions. This choice affects strength, durability, and how the shell interacts with seawater chemistry. Over long time, it can even influence what is preserved in fossils, because one form may be more likely to transform or dissolve. When you hold a shell, you are holding a biological decision that reached all the way down to crystal structure. It is not only a shape made by an animal. It is also an arrangement made by physics and chemistry, guided by life. Ice has many crystal phases, some forming only under extreme pressure. We think of ice as simple, but water is famous for being strange, and its crystals are part of that strangeness. Under everyday conditions, ice forms a familiar structure, the one that makes snowflakes and frozen ponds. Yet when pressure rises, water can adopt entirely different crystalline arrangements, creating a whole family of ices with distinct internal patterns. Some form deep inside planets and moons, where gravity compresses water far beyond anything on Earth's surface. In those hidden worlds, ice can behave less like brittle winter frost and more like a dense mineral, with properties that reshape how heat moves and how layers settle. This means ice is not only a symbol of cold, it is a versatile solid that changes its identity under pressure, as if water keeps a private collection of crystal costumes for different environments. The next time you see ice in a glass, it is worth remembering that you are meeting only one member of a much larger, stranger family. Crystals often grow fastest at sharp edges, producing dramatic points. A crystal point can look like a deliberate sculpture, but its dramatic shape often comes from a simple advantage. Sharp edges and corners are hungry places, where atoms and molecules can attach more easily than they can on a flat face. Those edges act like busy doorways, so growth races ahead there first. As the tip extends, it stays exposed to fresh material, which keeps feeding the point. This is part of why crystals can look like they are reaching, as if the shape itself wants to stretch toward open space. It also explains why some crystals develop step-like patterns on their faces, marking episodes of faster growth and slower pauses. Crystal growth is not always smooth. It can surge, rest, and surge again as conditions change. When you see a long, clean point, you are seeing a history of tiny arrivals, each one choosing the easiest landing spot, building a shape that looks dramatic because physics makes edges irresistible. Some crystals form perfect cubes, like pyrite, fluorite, and salt. A cube feels almost too human, like something carved with a ruler. Yet in certain crystals, the cube is simply the most natural expression of their internal symmetry. When the atomic lattice has equal directions that repeat in a balanced way, the external faces that grow most steadily can meet at right angles, producing that unmistakable box shape. Pyrite is famous for this, sometimes forming clusters of cubes that look manufactured. Fluorite can do it too, creating stacks that seem like tiny architecture. The delight of cubic crystals is how they challenge our assumptions. They look artificial, but they are wildly natural. And the cube is not only a shape, it is a clue. It tells you about the repeating order inside, the way the material prefers to grow, and the conditions that allowed it to hold those faces without being broken or crowded out by neighbors. Nature can be startlingly geometric when it has the chance. Others grow as needles, plates, or prisms, shaped by atomic geometry. Not every crystal wants to be a block. Some stretch into needles, thin as eyelashes, because their structure makes growth much easier in one direction than in others. Others spread into plaits, like mineral pages, stacking layer on layer. Prisms appear when a crystal grows steadily along a central axis, keeping the same cross-section as it extends. These shapes come from differences in how strongly atoms bond on different surfaces. One face may be stable and slow to accept new material, while another face is eager and fast. The result is a crystal that seems to have a personality, leaning toward elongation, flattening, or steady column building. The environment adds its own influence too. Flowing fluids can deliver material unevenly, and limited space can force a crystal to adapt its outline. But the underlying guide is always the atomic blueprint. Geometry at the smallest scale quietly dictates the silhouette you can hold in your hand. Crystal twins are intergrown pairs, like two mirrored structures sharing one body. Sometimes a crystal begins to grow, and then the pattern flips, as if the structure decided to reflect itself in a mirror. The result is a twin. Two parts joined together in a specific, rule-bound way. This is not random tangling. Twinning follows precise relationships, and the joined crystal can display striking shapes that a single crystal could never make alone. Some twins look like arrows or butterflies. Others form repeated intergrowths that create ridges and grooves, making the surface look like it was folded. Twinning can happen because of a sudden change during growth, like a bump in temperature or chemistry, or because of stress that nudges the lattice into a new orientation. For collectors, twins can feel like personality made visible. For scientists, they are clues, evidence of the moment something shifted in the environment. A twin is a crystal telling you it lived through an event, and it recorded that event in its own geometry. A crystal can trap fluid bubbles, preserving ancient water like time capsules. As a crystal grows from a liquid, it can sometimes swallow a tiny pocket of that liquid, sealing it inside as growth continues. These trapped pockets are called fluid inclusions, and they are astonishing because they can preserve actual samples of ancient fluids locked away for millions of years. In some cases, that trapped fluid may include dissolved salts, gases, or microscopic particles that reveal what the environment was like when the crystal formed. It is like finding a sealed bottle from a long-vanished world, except the bottle is stone and the contents are older than human history. Researchers can study these inclusions to learn about temperatures, pressures, and the chemistry of the fluids that once moved through Earth's crust. And even without laboratory work, the idea is quietly thrilling. A clear crystal can hold tiny hidden droplets, each one a preserved moment, a physical memory of water that flowed through rock long before the modern landscape existed. Diamonds sometimes trap tiny minerals that reveal depths of Earth's mantle. Some diamonds contain microscopic passengers locked inside, while the crystal was still growing far beneath the surface. These trapped minerals are not flaws, but clues. Certain inclusions can only form under the immense pressures found deep in Earth's mantle, far below any drill or mine. When scientists study them, they can identify the conditions where the diamond formed, including depth, temperature, and surrounding chemistry. In this way, a diamond becomes a sealed message from a region humans cannot visit directly. The stone may travel violently upward in volcanic eruptions, yet the inclusions remain protected, unchanged for immense spans of time. What appears to be a simple gem can therefore hold direct evidence of Earth's deep interior. Each inclusion is a tiny witness, preserving information from a hidden world that would otherwise remain entirely out of reach. Zircon crystals can be older than most rocks, surviving immense geological recycling. Zircon is one of the most resilient minerals on Earth. While entire rocks can melt, fracture, or be reshaped by pressure, zircon grains often survive these events intact. They can be eroded from one rock, carried by rivers, buried in sediments, then later trapped inside new rocks formed under heat and pressure. This means a single, tiny crystal can pass through multiple geological cycles without losing its identity. Some zircons formed when Earth was still young, long before today's continents existed in their current form. Finding one is like discovering an ancient traveler hidden inside a younger landscape. Zircon's durability allows it to preserve information that other minerals lose, making it a quiet archive of deep time. Even when everything around it changes, zircon can endure, holding on to memories from chapters of Earth's story that would otherwise be erased. Tiny zircon grains help scientists date early Earth using uranium decay. When zircon crystals form, they readily accept uranium atoms into their structure, while strongly rejecting lead. This unusual preference turned zircon into a natural clock. Over time, uranium atoms slowly decay into lead at a known rate. By measuring the ratio of uranium to lead inside a zircon grain, scientists can calculate when that crystal first formed. Because zircon can survive intense geological processes, this clock often remains accurate, even when surrounding rocks have been altered or destroyed. Some of the oldest known evidence for Earth's early surface conditions comes from zircon grains preserved in much younger rocks. These tiny crystals have helped scientists piece together timelines reaching back billions of years. It is remarkable that something so small can carry such precise information. A zircon grain no bigger than sand can quietly record time with a reliability that rivals the most carefully engineered instruments. Meteorites contain crystals that formed before the sun fully ignited. Some meteorites preserve minerals that crystallized during the earliest moments of the solar system. Before planets existed, a swirling disk of gas and dust surrounded the young sun. Within that disk, heat and motion allowed minerals to condense directly from vapor, forming tiny crystals that would later become part of meteorites. These crystals predate Earth itself. They formed before the sun settled into stable light, and long before worlds took shape. When such meteorites fall to Earth, they deliver material that has traveled through space largely unchanged since that distant time. Studying these crystals allows scientists to reconstruct conditions present at the solar system's birth, including temperature ranges and chemical environments. Holding a meteorite is therefore not just holding a rock. It is holding a fragment of an unfinished beginning, a preserved remnant from a time when planets were only possibilities. Some crystals record magnetic fields as they grow, storing planetary history. Certain minerals can capture the direction and strength of a magnetic field during their formation. As these crystals grow, tiny magnetic components within them align with the surrounding field. Once the crystal solidifies, that alignment becomes locked in place, preserving a record of magnetism from that moment in time. Long after landscapes shift and continents drift, the crystal still holds that ancient signal. By studying these magnetic records, scientists can trace changes in Earth's magnetic field and even reconstruct the movement of tectonic plates. This information helps reveal how oceans opened, mountains rose, and magnetic poles reversed. What makes this so extraordinary is its subtlety. An invisible force leaves a permanent signature inside stone. A crystal becomes a memory device for the planet itself, quietly recording directions and strengths long after the field that shaped it has changed or vanished. Crystals can host color centers, where missing atoms change light absorption. Color does not always come from added ingredients. In some crystals, it comes from absence. If an atom is missing from the lattice, it can leave behind a small imbalance that traps an electron. That trapped electron can absorb specific wavelengths of light, producing visible color. These sites are called color centers, and they can form through natural radiation, heat, or energetic events that disturb the crystal's structure. A crystal may appear clear at first, then gradually develop color as these centers accumulate. What is striking is how small the cores can be. A tiny number of altered sites can tint an entire stone. Color centers show that crystals are not inert. They respond to their environment and record what they experience. Light passing through the stone reveals that history, turning invisible atomic changes into visible hues. A single trace impurity can transform a clear crystal into a gemstone. Many gemstones owe their beauty to impurities so scarce they barely register chemically. A few foreign atoms slipping into a crystal lattice can dramatically alter how light is absorbed and transmitted. These trace elements replace or accompany the original atoms, subtly changing the crystal's electronic behavior. The result can be a vivid color that dominates the stone's appearance. Without those impurities, the same mineral might look completely ordinary. This transformation highlights how sensitive crystals are to their internal makeup. Beauty can emerge not from abundance, but from precision. A tiny difference at the atomic scale becomes a bold visual effect at the human scale. Gemstones are therefore not just minerals. They are records of unlikely encounters, moments when rare ingredients met the right structure at the right time. Their color tells a story of chance, chemistry, and remarkable amplification. Opal is not a true crystal, but ordered spheres that diffract light. Opal's shifting colors come from structure rather than pigment. Instead of a repeating crystal lattice, opal is made of tiny silica spheres stacked in an orderly arrangement. When light enters the stone, these spheres bend and scatter it, separating colors through diffraction. Different viewing angles reveal different flashes, creating the moving play of color that opal is known for. The effect depends on the size and regularity of the spheres. If they are uneven, the color fades. If they are well ordered, the stone comes alive. Opal also contains water, which makes it more delicate than many gemstones. This combination of fragility and brilliance gives opal a unique character. It is not built from rigid repetition, but from careful arrangement. Opal shows that order does not always mean rigidity. Sometimes, beauty emerges from a softer, more flexible kind of structure. Labradorite flushes color because light scatters within layered crystal structures. Labradorite can appear plain until it catches light at just the right angle. Then, sudden flashes of blue, green, or gold ignite beneath the surface. This effect comes from fine internal layers within the crystal that cause light to scatter and interfere. Certain wavelengths are strengthened, while others cancel out, producing metallic-looking color bursts that shift with movement. The color is not painted on and does not come from impurities alone. It is an optical response built into the crystal's structure. As you move the stone, the light changes, giving the impression that the crystal is alive. This quality has made labradorite especially captivating for jewelry and decorative use. It rewards motion and attention. The stone teaches a subtle lesson. Color can be dynamic, emerging from structure and perspective rather than fixed material alone. Moonstone shimmers from microscopic layers that split and recombine light. Moonstone glows softly rather than flashing brightly. Its sheen comes from extremely thin internal layers that scatter light beneath the surface. As light enters, it is gently split and recombined, creating a floating glow that seems to move as the stone is tilted. This effect is called adularescence, and it depends on precise spacing between layers inside the crystal. When those layers are just right, the light appears to drift like mist across the stone. Moonstone's beauty is quiet and restrained, relying on subtle interaction rather than bold color. Cutters often shape it carefully to enhance this moving glow. The result feels calm and lunar, as if the stone holds a small, steady light within. Moonstone reminds us that crystals do not need brilliance to captivate. Sometimes, softness and patience create the most lasting fascination. Bismuth forms stair-step hopper crystals because edges grow faster than faces. Bismuth crystals look almost designed, with sharp terraces that resemble tiny staircases or futuristic buildings. This shape forms because the edges of the crystal are the easiest places for new atoms to attach. As the crystal grows, the outer rim keeps extending, while the flat center fills in more slowly. Instead of becoming solid all at once, the structure builds its outline first, leaving hollowed steps behind. The process is not decorative, but efficient, driven by where atoms can settle most easily. Bismuth adds another layer of wonder through color. Its surface often shows shifting rainbow tones caused by a very thin oxide layer that forms as the crystal cools and meets air. Light reflects differently across that layer, creating shimmering colors without any pigment. One crystal ends up telling two stories at once, one about growth speed and structure, and another about how light responds to a changing surface. Selenite can grow into clear blades so large they look like frozen windows. In rare underground spaces, selenite crystals have grown to astonishing sizes, stretching longer than a person and glowing with a soft, glass-like clarity. These giants form when mineral-rich water remains warm and stable for extremely long periods. That steady environment allows gypsum to assemble slowly and evenly, without interruption. The result is a crystal with smooth faces and remarkable transparency. What makes this growth so striking is how sensitive it is to change. A sudden shift in temperature or chemistry can halt or distort the process. Because gypsum is soft, these large crystals are also fragile, easily scratched or damaged. Their existence depends on long-lasting calm. When you imagine a crystal that large, it stops feeling like an object and starts feeling like a place. It is not just something that grew. It is something that quietly occupied space, assembling itself molecule by molecule in darkness. Howite crystals can form in deserts, growing from nightly dew and evaporation. In some deserts, salt crystals can grow without deep time or dramatic geology. After sunset, cooling air allows moisture to condense, as dew or thin films of water on the ground. That moisture dissolves small amounts of salt already present in the soil. When the sun rises, heat quickly drives the water away. The salt remains behind and crystallizes, often forming tiny cubes and brittle crusts. Night after night, this simple cycle repeats. Over time, it can build shimmering salt flats and delicate plates that crunch underfoot. This process shows that crystal growth does not always require molten rock or ancient seas. Sometimes it only needs air, temperature changes, and patience. The desert becomes a quiet workshop where evaporation does the work. Salt crystals appear, disappear, and reappear, shaped by daily rhythms rather than deep geological events. Gypsum crystals can bloom in caves, building delicate blades from mineral water. Some caves host gypsum formations that look like frozen flowers or sprays of thin white blades. These form when groundwater carrying dissolved minerals enters open cave spaces and slowly loses the ability to keep those minerals dissolved. Crystals begin growing outward from walls and floors, forming fans, needles, or feathery clusters. Caves provide ideal conditions for this growth. They are sheltered from wind, sunlight, and strong temperature changes, allowing fragile structures to survive. Many gypsum blooms are extremely delicate and can break with the lightest touch. That fragility makes them feel temporary, even though they may have taken immense time to form. Each blade records repeated moments of mineral delivery and quiet deposition. The result is stone that seems to behave like frost or petals, growing slowly in darkness, shaped by stillness rather than force. Stalactites and stalagmites grow by crystallizing calcium carbonate drop by drop. Cave formations built by dripping water are monuments to patience. As water moves through limestone, it dissolves small amounts of calcium carbonate. When that water enters an open cave, conditions change, and a tiny portion of the mineral crystallizes out. On the ceiling, this builds a stalactite. On the floor below, it builds a stalagmite. Each drop leaves behind an almost invisible layer. Over long stretches of time, those layers accumulate into shapes you can walk around. Some formations show subtle banding that reflects changes in water chemistry or flow. When a stalactite and stalagmite finally meet, they form a column, closing the space between ceiling and floor. It is easy to forget how gentle the process is. No single drop seems important, yet together they build structures that feel permanent, shaped entirely by repetition and quiet chemistry. In volcanic gas, crystals can grow directly from vapor, not liquid. Near volcanic vents, minerals can form in a way that defies everyday expectations. Hot gases rising from the earth can carry chemical ingredients as vapor. When those gases cool or react with air, solid crystals can deposit directly onto rock surfaces. This process skips the liquid stage entirely. Around fumaroles, bright crusts and delicate crystal coatings can appear, sometimes changing quickly as conditions shift. These crystals form in harsh environments filled with heat and corrosive gases, yet they can grow with surprising intricacy. Their existence is often temporary, appearing and vanishing as volcanic activity changes. This makes them feel like moments rather than monuments. Crystal growth here is fast, reactive, and alive. It reminds us that crystals are not limited to calm settings. They can form in breath like plumes of gas, shaped by energy, chemistry, and motion. Some hot springs build bright terraces by crystallizing minerals from flowing water. Certain hot springs create step terraces that look sculpted by design. As hot water rises, it carries dissolved minerals. When it reaches the surface, cooling and chemical changes force those minerals to crystallize along the water's path. Thin deposits build up at edges and lips, creating basins that guide the flow into new channels. Over time, the spring constructs its own layered landscape. Many terraces are also colored by heat-loving microbes that thrive in warm water, adding oranges, greens, and browns. The result is a living structure shaped by both chemistry and biology. These formations are not fixed. They grow, crack, and shift as water finds new roots. A hot spring terrace is a record of movement, showing how flowing water can slowly turn itself into stone. Crystals can form inside lava bubbles, making tiny mineral gardens in basalt. When lava cools, gas bubbles can become trapped, leaving hollow pockets inside the solid rock. Long after the lava hardens, groundwater may seep through the basalt carrying dissolved minerals. Inside those small cavities, crystals can begin to grow along the walls. Over time, the once empty bubble becomes lined with sparkling points or thin mineral layers. These hidden spaces can turn ordinary-looking rock into a surprise when broken open. The contrast is striking. Dark, heavy basalt on the outside can hide delicate structures within. These mineral gardens form quietly, long after the drama of eruption has passed. They show that rocks continue evolving even after they appear solid and still. Empty space becomes opportunity, and crystals move in to fill it. Coral reefs are built from living animals that crystallize calcium carbonate skeletons. Coral reefs may look like stone, but they are built by living animals. Tiny coral polyps extract calcium and carbonate from seawater and use it to build hard skeletons beneath their bodies. As generations grow, die, and grow again, these skeletons accumulate into massive reef structures. The reef becomes a foundation for entire ecosystems, sheltering countless species. This crystal building process is sensitive to ocean conditions. Temperature and water chemistry affect how easily corals can build and maintain their skeletons. That makes reefs both beautiful and vulnerable. They are living records of environmental balance. A reef is biology acting as geology, using crystal growth to shape coastlines and create habitats. It is one of the clearest examples of life using mineral processes to build something far larger than itself. Your bones and teeth are reinforced with crystals of hydroxyapatite. Inside your body, crystals provide strength. Bones and teeth are reinforced by hydroxyapatite, a mineral made from calcium and phosphate that forms tiny crystals within a flexible protein framework. In bone, this combination creates material that is strong yet slightly elastic, able to handle daily stress. Teeth take mineral reinforcement even further. Enamel is densely packed with crystals, making it one of the hardest substances your body produces. This crystal structure resists wear and protects sensitive inner layers. What makes this remarkable is that the process is active. Bone is constantly broken down and rebuilt, adjusting its structure in response to use and injury. Your skeleton is not static stone. It is a living crystal system, carefully managed and continuously renewed. Many animals make crystals to sense gravity using tiny inner ear stones. Deep inside the ears of many animals sit tiny crystals that act like a built-in compass for up and down. These grains are often calcium carbonate, and they rest on delicate sensory hairs. When an animal tilts its head or accelerates, the crystals shift slightly, bending those hairs and sending signals to the brain. That is how you can know which way is upright even with your eyes closed. Fish, reptiles, birds, and mammals all rely on versions of this system, though the exact shapes and arrangements vary. It is wonderfully simple, almost like carrying a tiny bag of stones that gently tug on sensors whenever you move. When these crystals become disturbed or misplaced, the world can feel like it is spinning, which shows how important they are. Gravity is invisible, but these inner crystals translate it into touch. Some insects include crystals in their eyes to manipulate and focus light. Insect eyes are not built like ours, and that is part of their magic. Many insects have compound eyes made of many small units, and within those units they can use crystalline materials to guide light where it needs to go. In some species, crystals help act like tiny lenses, shaping the light path, so the insect can form a usable image from many small samples. Other structures can control how different wavelengths are handled, improving contrast or reducing glare. This is not decoration. It is optical engineering made from biology. The result can be vision that is excellent at detecting motion, even if it is not high resolution in the human sense. It is also a reminder that crystals are not only in rocks. Living creatures can grow ordered structures for practical reasons, turning the rules of light into tools for survival. A flying insect does not just see the world. It sculpts incoming light first. Certain fish have guanine crystals that create shimmering, mirror-like skin. Some fish look like living mirrors, flashing silver as they turn, and the shine often comes from stacks of guanine crystals in their skin. Guanine is a building block related to DNA, but in this case it is used as a reflective material. The crystals form thin plates arranged in layers, and those layers reflect light with impressive efficiency. This can help a fish blend into its surroundings, because a mirror-like surface can reflect the brightness of the water around it, making the body harder to spot. It can also confuse predators by creating shifting glints that make it difficult to track movement. The effect depends on spacing, alignment, and thickness, so the shimmer is not accidental. It is built. When a school of fish turns together, the light ripples across them like a single bright wave, powered by countless microscopic crystal plates. A chameleon's color shifts partly through crystal-like structures that change spacing. Some chameleons change color not only by moving pigments, but also by adjusting tiny structures in their skin that behave like tunable crystal arrays. In certain layers, cells contain nanoscale features that can shift their spacing. When the spacing changes, the skin reflects different wavelengths of light, so the visible color can shift from greens toward yellows, oranges, or blues depending on the pattern. This is a physical way of making color, based on structure rather than dye. It is also responsive. Changes in mood, temperature, or social signals can influence the skin's state, turning the animal into a living display that can communicate without sound. The fascinating part is that the color is not painted on the surface. It is created by light interacting with a changing internal arrangement. A chameleon becomes a moving lesson in how geometry can control what the eye sees. Butterflies often use photonic crystal structures, not pigments, for brilliant blues. Many vivid butterfly blues are not made by blue pigment at all. Instead, the wings contain microscopic structures that act like photonic crystals, repeating patterns that reflect certain wavelengths strongly. Light hits the wing scales, bounces through tiny ridges and layers, and specific colors emerge while others fade. This is why some butterfly blues can look so intense and so clean, and why they can shift slightly with viewing angle. The color comes from architecture. In some cases, even crushed wing scales keep their color because the structure remains, while pigments would smear or dull. These structural colors can be so efficient that they inspire engineers designing low-energy color surfaces and security features. What feels like a simple splash of beauty is really a carefully evolved optical device. The wing is both art and instrument, built from repeating patterns too small to see, yet loud enough to glow across a garden. Protein crystals let scientists map biology by bending X-rays into patterns. To understand a protein's shape, scientists sometimes coax it into forming a crystal. That sounds surprising because proteins feel soft and alive, not like minerals. But when many identical protein molecules pack into a repeating arrangement, they create an ordered grid. If X-rays are shone through that grid, the rays scatter into a pattern of spots, like a shadow made from symmetry. From that pattern, researchers can infer the protein structure, revealing how it folds and where it might interact with other molecules. This matters because shape is often the key to function. A tiny pocket in the structure can be where a drug binds. A subtle twist can control activity. Growing a good protein crystal can be difficult, and it can take careful control of salt, temperature, and concentration. Yet when it works, the reward is a blueprint of life at molecular scale, derived from order and light. Crystallography revealed DNA's structure by interpreting diffraction from ordered molecules. One of the great scientific reveals of the 20th century depended on a simple idea. If a molecule is arranged in an orderly way, it can scatter X-rays into a pattern that carries information about its shape. Early researchers used diffraction images from ordered DNA fibers to infer key features of its structure, including the helical arrangement and repeating distances. The images themselves were not a direct photograph of the molecule. They were clues that required careful interpretation, patience, and math. But those clues were powerful enough to change biology forever. Once the double helix became clear, it reshaped how people understood inheritance, mutation, and the way information is stored in cells. It is striking to think that the secret of life's instruction book was uncovered by studying how X-rays interact with order. A repeating pattern, invisible to the eye, left a visible signature on film. Structure announced itself through symmetry. Medicines can change behavior if they crystallize differently inside a tablet. A tablet may look simple, but inside it, the crystal form of the active ingredient can shape how the medicine behaves. The same molecule can sometimes pack into different crystal arrangements, and those arrangements can dissolve at different rates. That matters because dissolving controls how quickly the medicine becomes available in the body. A faster dissolving form might act sooner, while a slower form might release more gradually. Manufacturers work carefully to control crystal form, particle size, and how ingredients are processed, because small changes can affect stability on the shelf and performance after swallowing. Sometimes a medicine can even shift form over time if conditions are wrong, such as humidity or temperature swings. This is why quality control in pharmaceuticals is so strict. In a quiet way, crystals sit at the center of modern healthcare. The effect is not mystical. It is physical. The way molecules line up can influence how relief arrives. Chocolates snap and shine depend on which cocoa butter crystals form. Chocolate is a delicious lesson in crystal science. Cocoa butter can solidify into several different crystal forms, and only one of them gives the glossy surface, clean snap, and smooth melt people love. Tempering is the process of guiding chocolate toward that preferred form by carefully heating and cooling so the right seed crystals appear and grow. If the wrong forms dominate, the chocolate can turn dull, soft, or crumbly. Over time, it may develop a pale coating called bloom when fats migrate and recrystallize on the surface. That bloom is safe to eat, but it is a visible sign that the internal crystal balance has shifted. What is charming here is that a familiar treat depends on invisible order. The pleasure of a crisp break and a silky melt comes from how molecules pack together while cooling. Chocolate is not only flavor, it is structure you can hear and feel. Sugar crystals can grow in rock candy, turning syrup into edible geometry. Rock candy begins as a supersaturated sugar solution, meaning more sugar is dissolved than would normally stay dissolved at that temperature. As the solution cools and rests, sugar molecules begin seeking stable places to attach, and a crystal can start growing around the string or stick. Over days, the crystal expands outward, building faceted shapes you can see clearly. The process feels almost like watching order emerge from sweetness. You can influence the result by how concentrated the syrup is, how still it remains, and how clean the starting surface is. Even tiny vibrations can affect growth, because crystals prefer calm. What you end up with is edible geometry, a visible reminder that crystal rules apply in kitchens as much as they do in caves. Each crunchy facet is a record of repeated molecular arrivals, settling into place one by one, until a simple liquid becomes a solid you can hold up to the light. Silicon crystals form the heart of computer chips, grown as near-perfect cylinders. Modern computing begins as something that looks almost like a polished tree trunk. A near-perfect silicon crystal is grown into a long cylinder with atoms aligned in one continuous pattern. This is not a casual melt and cool. It is careful crystal farming, where a tiny seed crystal is dipped into molten silicon and slowly pulled upward while rotating. The goal is purity and consistency, because even small disruptions can change how electricity moves through the material. The result is a single crystal that can be measured in length and weight, yet is ordered down to the atomic scale. It is quietly astonishing that the apps, music, maps, and messages in daily life trace back to this calm industrial ritual. Before there are circuits or transistors, there is a cylinder of crystal grown with patience, like a manufactured mineral made to be as regular as nature and often more controlled. A single silicon crystal can be sliced into wafers for thousands of processes. Once a single crystal cylinder is grown, it is not used as one chunk. It is sliced into thin, round wafers, like turning a crystal loaf into many identical pieces. Each wafer becomes a stage where complex patterns will later be etched and layered, building tiny components that act like switches, gates, and memory. The wafer must be smooth and clean beyond everyday intuition. It is polished until it becomes a mirror, because tiny bumps can ruin tiny features. Then comes a long sequence of steps that add and remove materials in precise patterns. A single wafer can hold many identical chips, which are later separated like squares on a sheet. This scaling is part of the wonder. One carefully grown crystal can seed an enormous amount of technology, multiplying into thousands of processors that travel around the world inside phones, cars, appliances, and servers. A single slice of crystal becomes a whole library of computation. Solar panels often use crystalline silicon, turning light into moving electrons. A solar panel can look still and quiet, but inside it light is constantly being translated into motion. Crystalline silicon is arranged into a structure that helps create an electric field at a junction, often where two differently treated layers meet. When sunlight strikes the material, it can give electrons enough energy to break free from their usual positions. The built-in field nudges those electrons in a preferred direction, and that directed flow becomes electric current. What feels magical is how direct it is. Photons arrive from the sun, and electricity leaves the panel without any spinning parts. Crystal quality matters because defects can trap electrons and waste energy as heat. That is why solar manufacturing cares about purity, grain boundaries, and careful processing. A solar panel is not just glass on a roof. It is a carefully arranged crystal system that turns daylight into usable power, one absorbed photon at a time. Perovskite crystals are reshaping solar research with rapid efficiency gains. Perovskites have become a star of solar research because they can be made in ways that feel almost too convenient compared to traditional silicon. These materials form crystalline structures that absorb light very strongly, so thin layers can do a lot of work. Researchers have learned to tune perovskite chemistry to adjust what colors of light it captures, and to improve how charges move through the crystal. This has led to rapid jumps in solar cell efficiency over a relatively short research timeline. The excitement is not only about performance, it is also about possibility. Perovskites can be processed at lower temperatures and potentially deposited in flexible formats, which suggests new kinds of lightweight solar surfaces. The big challenge is stability, because some formulations can degrade with moisture, heat, or long exposure to sunlight. That tension makes the story compelling. A crystal with dazzling promise must also learn endurance. Perovskites are a reminder that crystal science is an active frontier, not a finished chapter. Gallium nitride crystals power bright LEDs and fast chargers. If you have noticed how modern LEDs can be intensely bright while staying efficient, gallium nitride is part of that story. This crystalline semiconductor handles high power and high frequencies well, making it valuable for both lighting and power electronics. In LED, it helps create devices that convert electrical energy into light with impressive efficiency and long lifetimes. In chargers, gallium nitride components can switch electricity rapidly with reduced energy loss, which is one reason some newer chargers can be smaller, cooler, and more powerful than older designs. The crystal itself must be grown and engineered carefully, because small defects can affect performance. What makes this fascinating is the everyday reach. A hard, carefully made crystal becomes the reason a street light looks crisp at night, or a compact charger refuels your devices quickly. It is a quiet upgrade to modern life, delivered through crystal structure and precise manufacturing. Sapphire crystals can be used as tough windows for scanners and optics. Sapphire is not only a gemstone. It is also a remarkably tough crystal that can serve as a durable window in demanding devices. Because it is hard, scratch-resistant, and optically clear across useful ranges, sapphire can protect sensitive components while still letting light pass through. That makes it valuable in scanners, watches, and certain optical systems where a surface must survive constant contact. Unlike ordinary glass, sapphire resists abrasion from dust and grit, which matters in industrial settings and outdoor environments. It can also tolerate heat and chemical exposure better than many transparent materials. What is delightful here is the shift in meaning. A crystal associated with jewelry becomes a practical shield for modern instruments. It is protection you can see through. Behind a sapphire window, sensors read barcodes, measure light, or track alignment. The crystal is doing a humble job, but it does it with gemstone strength, proving that beauty and utility can share the same lattice. Diamond crystals can spread heat so well they protect high-power electronics. Diamond is famous for sparkle and hardness, yet one of its most impressive talents is invisible. It can conduct heat extremely well, moving thermal energy away from hotspots faster than many other materials. In high-power electronics, heat is often the limiting factor. Too much heat can distort performance, shorten lifetime, or cause sudden failure. Using diamond as a heat-spreading material can help pull heat away from delicate components, keeping them within safe operating ranges. This is not about luxury. It is about survival under stress. Engineers can use diamond films or diamond-based composites in specialized applications where heat management is critical. The crystal lattice that makes diamond strong also provides a pathway for vibrations in the material to carry heat efficiently. It is a lovely reversal. We tend to think of crystals as fragile. Here, a crystal acts like a protective thermal highway, quietly guarding the devices that run intense currents and fast signals. Quartz crystals stabilize radio frequencies, helping signals stay locked and clear. Radio communication depends on steady timing. If a transmitter or receiver drifts, signals become harder to tune and harder to decode. Quartz helps solve this through its ability to vibrate at extremely stable frequencies when connected to an electronic circuit. A properly cut quartz crystal acts like a resonator, favoring one narrow frequency the way a tuning fork favors one note. Circuits use that steadiness to keep oscillations locked, so radios, transmitters, and many communication devices can stay on channel. The wonder is how physical and simple it is. A small slice of mineral, cut at a specific orientation, becomes the anchor for invisible waves traveling through air. Different cuts and designs can reduce sensitivity to temperature changes, making the frequency even more reliable in real environments. Quartz does not send the message by itself. It keeps the rhythm steady enough that messages can travel faithfully. In a noisy world of signals, a crystal provides calm. Liquid crystals are not solid, yet they urbanize enough to control screens. Liquid crystals live in a strange middle state. They can flow like a liquid, yet their molecules keep a shared orientation, like a crowd that moves freely but still faces the same direction. That partial order makes them extremely useful. When an electric field is applied, the molecules can rotate or shift alignment, changing how they affect passing light. This ability to respond smoothly and reversibly is what allows many displays to show images by controlling brightness and color at each pixel. The beauty of liquid crystals is their balance. Too much freedom, and you lose control. Too much rigidity, and you lose responsiveness. In that middle state, they become a material that can be steered. It is crystal behavior without crystal hardness. The result is something deeply modern. A screen is not only electronics. It is a carefully managed dance of molecules, repeatedly aligning and relaxing as images appear and disappear. Many phone displays work by twisting liquid crystals to block or pass light. A common display approach begins with a bright backlight and a set of polarizing filters. Between them sits a thin layer of liquid crystal. In one state, the molecules twist the polarization of light so it can pass through the second filter and appear bright. When voltage is applied, the molecules reorient, the twist changes, and the light is blocked, making that pixel dark. Add color filters and finely controlled voltages, and the same principle produces full images with smooth gradients. The cleverness is how quietly it happens. No pixel is a tiny lamp that turns on and off by itself. Instead, each pixel is a gatekeeper deciding whether light may pass. The responsiveness depends on molecular alignment, temperature, and the quality of the liquid crystal layer, which is why displays are engineered so carefully. What looks like a simple tap on glass triggers a microscopic reordering that reshapes light in real time, creating motion, text, and color from controlled twists. Piezoelectric crystals power emission sparkers, turning a click into a flash. Inside many lighters, a crystal performs a tiny act of energy conversion that feels like a magic trick. When you press the button, a spring releases a small hammer that strikes a piezoelectric crystal. That sudden squeeze shifts charges inside the crystal's orderly lattice, creating a brief surge of high voltage. The voltage does not last, but it is strong enough to jump a narrow gap and become a spark you can see. There is no battery hiding inside, and no slow build-up of electricity beforehand. The power comes from your finger, delivered as a quick impact, and translated instantly into light and heat. The best part is how repeatable it is. The crystal does not wear out after one flash. With each click, it answers the same way, turning a moment of pressure into a bright, reliable ignition. Ultrasound machines use crystals that pulse when electricity hits them. Ultrasound makes images by turning the body into a landscape of echoes. At the center of the probe is a crystal that can convert electrical energy into vibration, and then convert vibration back into electrical signals. A short electrical pulse makes the crystal flex by a tiny amount, launching a burst of high-frequency sound into tissue. That sound travels, reflects off boundaries, and returns as faint echoes. The returning vibrations press on the crystal, which responds by producing matching electrical signals. A computer measures how long each echo took to come back and how strong it was, then builds a picture line by line, as if drawing with time. It is remarkable how gentle this can be, while still revealing motion, depth, and shape. A beating heart, a shifting tendon, a developing baby, all become visible because a crystal can speak in sound and listen in sound with steady precision. Microphones can use crystal sensors to convert vibrations into electrical signals. Some microphones do not mainly listen to air. They listen to contact and vibration, using a crystal as the translator. When a surface trembles even faintly, that motion presses on a piezoelectric element. The crystal responds by producing a changing voltage that mirrors the pattern of the vibration. This is why contact microphones can pick up the secret voice of objects, like the buzzing of a lampshade, the creak of a table, or the deep resonance of a guitar body. Musicians use crystal pickups to capture the character of an instrument directly through its wood and bridge, not just through the air around it. The result can feel close and intimate, like hearing the instrument from the inside. It is also a reminder that sound is not only something that travels through air. Sound is motion moving through matter, and a crystal can turn that motion into a signal ready to be shaped, amplified, and recorded. Some sensors detect tiny motions using crystal oscillations that shift in frequency. A vibrating crystal can act like a steady heartbeat for a machine, and that steadiness is exactly what makes it so sensitive. Engineers drive a crystal to oscillate at a precise frequency, then monitor it for the slightest drift. If a tiny mass settles on the surface, if temperature changes, if pressure shifts, or if a thin film of a chemical sticks to it, the crystal's rhythm nudges by a small amount. That change is measurable, and it can reveal events that would otherwise be invisible. This principle is used in sensors that detect trace chemicals, fine particles, or subtle mechanical strain. The crystal does not need to move dramatically. It only needs to keep time reliably. When the baseline is calm, even a whisper of change shows up as a shift in frequency. In a quiet way, the sensor becomes a listener for the microscopic world, translating tiny influences into readable differences in rhythm. Crystal resonators help GPS receivers lock onto precise timing signals. GPS feels like geography, but underneath it is a timing puzzle. Your receiver listens for signals from multiple satellites and compares when each one arrives. The differences in arrival times become distances, and the distances become position. To do that reliably, the receiver needs a stable internal rhythm that does not wander while it tracks faint radio codes. A crystal resonator provides that steadiness, acting like an electronic reference beat. It helps the receiver stay locked onto signals that may be weak, bouncing around buildings, or changing as you move. The crystal does not measure your location directly. It simply keeps time well enough that the receiver can do the math without losing its grip. That is what makes it so fascinating. A small piece of orderly mineral can help your phone listen to space with the calm precision needed to guide a walk through a city or a drive across a country. Synthetic gemstones are real crystals grown in labs with controlled conditions. A lab-grown gemstone is not a fake crystal. It is a crystal formed by the same rules, with the same structure and chemistry, just with a different birthplace. In a laboratory, scientists control temperature, pressure, and the chemical environment so atoms can assemble into an ordered lattice. This can produce stones with consistent color and clarity, and it can also reveal something deeply satisfying about crystals. They do not require mystery to form. They require conditions. When those conditions are met, order appears. Lab growth also reduces the randomness of natural formation, where cracks, inclusions, and uneven chemistry are common. Some people love those natural quirks. Others prefer a cleaner look. But either way, the science is the same. The crystal lattice determines the identity of the gem, not the story we attach to it. Watching a gemstone grow under controlled conditions is like seeing geology sped up and guided, with beauty arriving through patience and precision. A lab-grown diamond is still diamond, just with a different origin story. Diamond is defined by its structure. Carbon atoms bonded in a rigid three-dimensional network. When that structure forms, the material behaves as diamond, whether it grew deep in the earth or inside a chamber built by humans. In laboratories, diamonds can be made by recreating high-pressure conditions or by feeding carbon-rich gases onto a growing surface, letting the lattice build layer by layer. The result is the same kind of crystal, with the same hardness and the same way of handling light. What changes is the journey. Natural diamonds often carry a deep earth history and a violent trip upward. Lab-grown diamonds carry a story of controlled growth, careful monitoring, and deliberate design. That contrast can be surprisingly thought-provoking. Two stones can be physically equivalent, yet one is a geological messenger and the other is a technological achievement. In both cases, the wonder is the same. Carbon found a way to lock itself into one of nature's most famous and demanding patterns. Scientists grow gigantic crystals to study neutrons, magnetism, and superconductors. Some of the most important crystals in science are not worn, displayed, or collected. They are grown as large, extremely uniform single crystals, so researchers can probe how matter behaves. When a material is made of many tiny grains, boundaries and disorder can blur the signal. A single crystal provides clarity, a clean stage where internal patterns can be measured. In neutron scattering experiments, beams pass through the crystal and reveal how atoms are arranged and how they move. Other studies focus on magnetism, where subtle alignments and phase changes can be hidden unless the crystal is exceptionally well formed. For superconductors, crystal quality can determine whether unusual electrical states appear clearly or get masked by defects. Growing these crystals is slow and demanding, requiring controlled temperatures and high purity. It can feel like careful cultivation rather than manufacturing. The reward is profound. A large crystal becomes a scientific instrument made of the material itself, allowing nature to explain its own hidden rules. Superconducting crystals can carry current with almost no resistance when cooled. In everyday wires, electrical current loses energy as heat because electrons scatter as they move through the material. In a superconductor, that familiar loss can nearly vanish when the material is cooled below its critical temperature. The change can be sudden, like a door opening. Current flows with astonishing efficiency, and magnetic behavior shifts in dramatic ways, including the ability to push magnetic fields out of the interior. Many superconductors are crystalline materials, and their internal order helps determine whether this delicate state can form and remain stable. Cooling matters because heat causes atoms to vibrate, and those vibrations disrupt the coordinated motion needed for superconductivity. When the vibrations quiet down, a new kind of electrical behavior becomes possible. The result is one of the most striking reminders that matter has phases we do not encounter in daily life. With the right structure and the right temperature, a crystal can enter a regime where ordinary resistance fades and electricity behaves with almost dreamlike smoothness. Quasi-crystals show order without repeating patterns, once thought impossible in solids. For a long time, many scientists believed that a crystal's order had to repeat regularly, like tiles covering a floor. Quasi-crystals changed that assumption. They show clear order, with sharp diffraction patterns that prove atoms are arranged by rules, yet the pattern does not repeat in the usual periodic way. It is organized without looping back exactly. Some quasi-crystals even display symmetries that once seemed forbidden for crystal structures, forcing a rethink of what counts as crystalline order. This is not just a curiosity. Quasi-crystals can have unusual physical traits, including distinctive friction behavior and surprising ways of conducting heat. They sit between the comfort of repetition and the chaos of randomness, offering a third option that feels almost philosophical. Nature can build solids that are disciplined but not repetitive, structured but not predictable in the old sense. A quasi-crystal is a reminder that even in the solid state, matter can still surprise us with new kinds of order. Some metals crystallize into grains, and those grains shape strength and ductility. Inside a solid metal, atoms are not arranged as one continuous crystal. Instead, they form many tiny crystals called grains, each oriented slightly differently from its neighbors. The boundaries where these grains meet play a powerful role in how the metal behaves. When you bend or stretch metal, defects move through the crystal structure, and grain boundaries can slow or block that motion. Smaller grains usually make a metal stronger because there are more boundaries to interrupt movement. Larger grains can allow easier shaping but may reduce strength. This is why metals can feel stiff, springy, or soft, depending on how they were processed. Rolling, forging, and controlled heating all change grain size. Even a simple paperclip owes its behavior to this hidden mosaic of crystals. The metal you touch feels uniform, but its strength, flexibility, and failure all depend on how countless microscopic grains share the load together. Steel becomes tougher by controlling crystal phases formed during heating and cooling. Steel is unusually adaptable because its crystal structure can change with temperature. When heated, steel enters a phase that can dissolve more carbon within its lattice. As it cools, that structure transforms again, and the speed of cooling determines what forms next. Slow cooling allows atoms time to settle into softer arrangements. Rapid cooling can trap carbon in place, creating a harder but more brittle structure. A later reheating step, called tempering, adjusts the balance, restoring toughness while keeping strength. These changes happen entirely inside the crystal lattice, invisible from the outside. This is why the same steel recipe can produce a flexible spring, a sharp blade, or a structural beam. The craft lies in timing and temperature, not ingredients alone. Steel is not fixed by what it is made of, but by how its internal crystals are guided through carefully chosen thermal journeys. Turbine blades can be made as single crystals to survive brutal heat. Turbine engines operate in conditions so extreme that ordinary metal would slowly deform and fail. One solution is to make critical components from a single crystal rather than many grains. Grain boundaries are weak points where heat, stress, and corrosion can concentrate. By eliminating those boundaries, a single crystal blade can resist creep and cracking far better at high temperatures. Engineers also align the crystal so its strongest directions face the greatest forces. Producing such a blade requires careful control during solidification, so the crystal grows as one continuous structure. The result is a component that can endure intense heat and rotation for long periods. This allows engines to run hotter and more efficiently, improving performance and fuel economy. It is remarkable that the survival of a roaring turbine can depend on atomic order chosen during growth. A single uninterrupted crystal becomes a defense against some of the harshest conditions machines can face. Magnetic crystals can store information, forming the basis of many memory devices. In certain crystalline materials, atomic spins align into tiny magnetic regions that can be switched between stable states. Each orientation can represent information, such as a stored 0 or 1. Writing data means flipping these regions in controlled ways. Reading data means detecting their direction without disturbing them. The crystal structure matters because it affects how stable these magnetic states are and how easily they change. Engineers design materials so information remains secure against heat and noise, while still allowing fast access. This approach has enabled massive data storage in compact devices. Entire libraries can be held as patterns of magnetic alignment far smaller than a grain of dust. The information is not stored as flowing electricity, but as physical order frozen into matter. Memory becomes a property of crystal structure itself, turning invisible atomic orientation into lasting digital records. Certain crystals can guide light in photonic circuits, like glass highways for photons. Light can be controlled much like electricity when crystals are structured carefully. In photonic circuits, repeating crystal patterns create pathways that allow certain wavelengths of light to travel while blocking others. These structures act like microscopic road systems for photons, guiding them around bends, splitting them, or filtering them by color. Because light moves quickly and generates less heat than electrical currents, photonic circuits offer advantages for communication and sensing. The behavior comes not from mirrors or lenses, but from geometry written into the crystal itself. The spacing and arrangement determine how light flows. Shrinking optical control to this scale allows precise manipulation on chips. Information can be carried as light pulses instead of electrons. In this way, crystal structure becomes an architect for light, shaping its movement through carefully arranged order rather than through bulk materials. Crystals can polarize light, creating the Kahn glare reduction in some sunglasses. Reflected light from flat surfaces often vibrates in a preferred direction, creating glare that overwhelms vision. Polarizing filters work by blocking that orientation while allowing other light through. The effect feels calming, as harsh reflections fade and detail becomes clearer. Crystal-related ordering is essential to how these filters function, enforcing directional rules on incoming light. Instead of dimming everything equally, polarization selectively removes the most troublesome reflections. This makes it easier to see into water, drive in bright conditions, or reduce eye strain. The process reveals that light has structure beyond brightness. Waves have direction as well as intensity. Crystals make that hidden structure visible by interacting differently with different orientations. Wearing polarized lenses is not just wearing darker glass. It is wearing a filter shaped by crystal order, quietly shaping which vibrations are allowed to reach your eyes. A crystal's cleavage can make it split along flat planes, like natural sheets. Some crystals break in predictable ways because their atomic bonds are not equally strong in all directions. Along certain planes, bonds are weaker, creating preferred paths where the crystal can split smoothly. This property is called cleavage. When stress is applied, the crystal separates along those internal planes rather than shattering randomly. This is why some minerals produce flat surfaces when broken. Cleavage reveals the crystal's internal architecture, exposing how atoms are connected. It can be helpful for shaping materials, but it can also cause unexpected breaks if struck poorly. Gem cutters must respect cleavage to avoid damaging stones. What makes cleavage fascinating is its order. Even in breaking, the crystal follows rules. The fracture is not chaos. It is a guided separation, showing that structure influences not only how a crystal grows, but also how it prefers to come apart. Mica cleaves into thin flakes so easily, it once served as early windows. Mica splits into sheets so thin they can bend without breaking. This happens because its crystal structure is layered, with strong bonds within each layer and weaker bonds between layers. As a result, mica can be peeled apart into smooth, transparent or translucent flakes. Before modern glass was widely available, these sheets were sometimes used as windows, especially where heat resistance mattered. Mica can tolerate high temperatures and remain stable where glass might crack. It also became valuable as an electrical insulator for similar reasons. The ease with which mica separates can feel surprising for a mineral. Stone usually resists splitting, yet mica cooperates. Its layers part cleanly, revealing shimmering surfaces that catch light softly. The material's usefulness comes directly from its crystal architecture. Mica behaves the way it does because its atoms agree to stack gently, rather than lock tightly together. Graphite's layered crystals let it slide, which is why pencils write. When you write with a pencil, you are leaving behind thin layers of graphite, not ink. Graphite is carbon arranged in flat sheets. Within each sheet, atoms bond strongly. Between sheets, the bonds are weak, allowing layers to slide easily. As the pencil moves across paper, those layers shear off and cling to the fibers, forming a visible line. The darkness depends on how much material transfers and how it scatters light. This same sliding property makes graphite useful as a lubricant in some machines. What feels like a simple tool relies on crystal physics. Carbon can be arranged in ways that make it soft and slippery or hard and rigid. Pencils take advantage of the slippery arrangement. Every written word is a small demonstration of layered crystal structure in action, translating atomic behavior into marks you can read. Diamonds resist scratching because their crystal bonds are extremely strong in every direction. Diamond's resistance to scratching comes from how its atoms connect. Each carbon atom bonds strongly to neighbors in a rigid three-dimensional network. There are no weak planes where layers can slide apart. Scratching requires breaking or shifting bonds, and in diamond, those bonds resist movement equally in all directions. This makes diamond exceptionally hard against abrasion. Hardness does not mean indestructible. A sharp impact can still cause chipping because other properties like toughness behave differently. But for resisting wear, diamond is unmatched. This is why diamond is used in cutting and grinding tools as well as jewelry. The fascination lies in contrast. The same element forms both soft graphite and hard diamond. The difference is not chemistry, but structure. Diamond's lattice refuses to yield under rubbing and wear, turning atomic order into extreme durability. Not all hard gems are tough, because crystal fractures can be unpredictable. Hardness describes how well a gem resists scratching, but toughness describes how well it resists breaking, and the two are not the same. Some very hard gems can still fracture suddenly when struck because stress travels through their crystal structure along hidden weak paths. These paths come from how atoms are arranged and bonded inside the crystal. When force lines up with those internal planes, a crack can form quickly and spread before the stone can absorb the energy. This is why some gems survive years of wear, yet fail from a single sharp impact. Jewelers and setters must understand this difference to protect stones during cutting and mounting. A gem's beauty often hides a delicate balance of strength and vulnerability. What looks indestructible at the surface can contain internal directions that demand respect. Toughness lives inside the lattice, not on the hardness scale alone. Gem cutters study crystal symmetry to maximize sparkle and reduce weak directions. Every crystal has symmetry that governs how light travels through it and how force moves within it. Gem cutters study that symmetry carefully before making the first cut. Facets are oriented so light reflects internally and returns to the eye instead of leaking away. At the same time, cutters avoid aligning edges with cleavage directions that could cause breakage. A successful cut balances brilliance and durability by working with the crystal's natural order. This is why the same rough stone can produce wildly different results in different hands. Cutting is not decoration. It is negotiation with atomic structure. The stone tells the cutter where it wants to be shaped, where it is strong, and where it is fragile. When symmetry is respected, the gem sparkles more and survives longer. The finished stone carries both optical beauty and structural wisdom, shaped by knowledge that lives far beneath the surface. The famous star effect in some gems comes from aligned needle crystals inside. Star gemstones owe their beauty to tiny needle-shaped crystals trapped during growth. These inclusions align along specific directions dictated by the host crystal's symmetry. When light enters the stone, it reflects off the needles and gathers into bright rays that cross at the surface. This effect only appears when the stone is cut into a smooth dome, allowing reflected light to concentrate rather than scatter. The number and orientation of rays depend on how many inclusion directions are present. In many sapphires and rubies, the needles are made of rutile, arranged with remarkable consistency. What makes this effect special is that clarity would destroy it. Without inclusions, there would be no star. The gem's most dramatic feature comes from internal structure, not perfection. As the stone moves, the star glides across its surface, turning hidden order into visible motion. Cat's eye gems shimmer from parallel inclusions that reflect light as a band. Cat's eye gemstones display a single luminous line that slides across the surface when the stone moves. This effect is created by countless parallel inclusions inside the crystal that reflect light in a focused way. When the stone is cut into a rounded shape, those reflections merge into a narrow band resembling a feline eye. Precision matters at every stage. The inclusions must be evenly spaced and consistently aligned, and the cut must be oriented exactly right. If anything is off, the eye weakens or disappears. Chrysoberyl is the most famous cat's eye gem, prized for its sharp, centered band. Like starstones, these gems turn internal features into visual drama. Their beauty is not painted on the surface. It is built from repetition, hidden within. Light reveals that order as motion, creating a living highlight that responds to every shift of the hand. Some crystals glow under ultraviolet light, a phenomenon called fluorescence. Under ultraviolet light, some crystals absorb energy and re-emit it as visible glow. This process is called fluorescence, and it can transform ordinary minerals into vivid displays of color. The glow occurs when electrons inside the crystal are excited by ultraviolet radiation and then fall back to lower energy states, releasing light. The color depends on impurities and defects within the lattice. Some crystals glow blue, others green, red, or white. Fluorescence is used to identify minerals and analyze gemstones, revealing features invisible in normal light. It also shows that crystals interact with energy in layered ways. What appears dull in daylight may burst into color under different conditions. The glow fades when the ultraviolet source is removed, but the memory of it lingers. Fluorescence reminds us that crystals store potential energy quietly, waiting for the right trigger to release it as light. Fluorite is named for fluorescence, though many minerals can glow too. Fluorite played a key role in the discovery of fluorescence, giving the phenomenon its name. Early observers noticed that fluorite emitted visible light after exposure to invisible radiation. Later research revealed that many minerals share this ability. Calcite, witherite, and some diamonds can all fluoresce, each for different reasons. The glow comes from trace impurities or structural defects that trap and release energy. Fluorite remains famous because it can show a wide range of colors and glow patterns, sometimes changing appearance dramatically under ultraviolet light. Its behavior helped scientists understand how crystals interact with energy beyond visible wavelengths. Fluorescence turned minerals into tools for studying atomic behavior. It also deepened appreciation for hidden properties that only appear under special conditions. A crystal can seem simple until the lighting changes. Then its internal structure announces itself in color, revealing complexity that daylight alone cannot show. Certain crystals change color in sunlight versus indoor light, called color change. Some gemstones appear to change identity when moved between lighting environments. This color change effect happens because the crystal absorbs specific wavelengths differently depending on the light source. Sunlight and indoor lighting contain different balances of colors. A crystal that absorbs red light strongly may appear green in daylight but shift toward red or purple indoors. The change is not a trick of the eye. It is a real interaction between the stone's structure and the light spectrum. Trace elements inside the crystal create absorption patterns that respond differently to various sources. This makes color-changed gems especially captivating because they feel alive to their surroundings. The stone seems to respond to time of day and place. Color becomes dynamic rather than fixed. What you see depends on how the crystal is fed with light, turning illumination itself into part of the gem's story. Alexandrite shifts from green to red because it absorbs different parts of the spectrum. Alexandrite is the most famous color change gemstone because its shift is strong and dramatic. In daylight, it appears green or bluish-green. Under indoor lighting, it turns red or purplish. This happens because chromium inside the crystal absorbs light unevenly across the spectrum. Some light contains more green and blue wavelengths, while incandescent light is richer in red. Alexandrite transmits what remains after absorption, so the dominant color changes with the source. The effect is sharp enough that the stone can seem like two different gems. This rare behavior made alexandrite famous shortly after its discovery. It also makes it a lesson in crystal optics. Color is not only about pigment, it is about interaction. Alexandrite does not create color. It filters it, revealing how a crystal's internal structure can reshape perception simply by changing the light around it. Heat treatment can alter crystal defects, changing a gem's color and clarity. Heating a gemstone can rearrange defects inside its crystal lattice. These defects influence how light is absorbed and scattered. When heat allows atoms to shift slightly, color centers can strengthen, weaken, or disappear. In some gems, heating deepens color. In others, it lightens or clarifies the stone. This process has been used for centuries, long before its atomic explanation was understood. The changes are permanent because the crystal settles into a new stable arrangement as it cools. Heat treatment does not add material. It adjusts what is already there. The practice reveals how sensitive crystals are to their internal state. A small rearrangement can transform appearance completely. When done carefully, heat enhances beauty while preserving structure. When done poorly, it can damage the stone. Heat treatment is controlled change, guiding a crystal to reveal its best version through carefully applied energy. Irradiation can also shift color centers, turning pale stones into vibrant hues. Irradiation changes gemstone color by altering the distribution of electrons within the crystal lattice. When exposed to controlled radiation, electrons can be displaced and trapped in new positions, creating color centers that absorb light differently. This can turn pale stones into vivid blues, greens, or other hues. The process mimics natural radiation exposure that some minerals experience underground over long periods. In laboratories, it is carefully managed to achieve predictable results. After irradiation, stones are often gently heated to stabilize the new color. The crystal itself remains the same material. Only the electronic arrangement changes. This shows that color can arise from energy history, not just chemistry. A gemstone carries a record of how it has been treated. Irradiation reveals how flexible crystal appearance can be when electrons are encouraged to settle into new configurations within an otherwise unchanged lattice. Scientists can grow crystals in space to reduce gravity-driven imperfections. On Earth, gravity subtly interferes with crystal growth by pulling heavier components downward and driving fluid motion around a growing structure. These movements can introduce uneven composition, internal strain, and defects. In microgravity, those forces are greatly reduced. Without strong convection or settling, atoms can arrive at the growing crystal more evenly, allowing cleaner internal order to form. Scientists have taken advantage of this environment to grow crystals aboard space stations, especially protein crystals used for biological research. Some of these space-grown crystals show clearer internal patterns than their Earth-grown counterparts, making them easier to study. The goal is not perfection, but understanding. By removing gravity as a variable, researchers can separate which flaws are unavoidable and which are gravity-induced. Space becomes a laboratory for quiet assembly, revealing how crystals behave when freed from one of the most constant influences they experience on Earth. Crystal growth can be guided by seeds, tiny starters that set orientation. Many large crystals begin with something very small, a seed crystal, that provides a starting pattern. This seed carries a specific atomic orientation, and as new material attaches, it follows that arrangement. The process encourages the entire structure to grow as one continuous crystal rather than many competing grains. This technique is widely used to grow silicon for electronics, gemstones for study, and large crystals for research. Without a seed, growth can begin randomly in multiple directions, creating boundaries and internal weaknesses. With a seed, growth becomes orderly and predictable. The seed does not force atoms into place. It simply offers an example, and atoms align naturally under the right conditions. This reveals something elegant about crystal behavior. Order spreads when it is given a clear beginning. A structure measured in kilograms can trace its orientation back to a tiny fragment that quietly set the direction for everything that followed. Crystals can form dendrites, branching shapes that look like frost patterns. Under certain conditions, crystals grow in branching forms called dendrites that resemble trees, snowflakes, or frost spreading across glass. These shapes appear when material reaches the growing crystal unevenly, favoring fast growth at tips and edges. As a branch advances, it intercepts more incoming atoms, which encourages further branching. The process repeats, producing intricate patterns that feel organic despite being governed by physical rules. Dendritic growth is common in freezing metals, ice formation, and some mineral deposits. The final shape depends on temperature, concentration, and how quickly material is supplied. A slight change can turn a compact crystal into a sprawling network. What makes dendrites fascinating is that they show order responding to imbalance. The crystal does not grow this way by choice. It follows the path that delivers material most efficiently. Complexity emerges naturally when conditions favor rapid, uneven attachment, turning simple rules into elaborate structure. Imperfect crystals can be more useful than perfect ones, thanks to controlled defects. Perfect crystals are rare, and in many technologies they would be less useful even if they were common. Small, intentional defects often give crystals their most valuable properties. In semiconductors, adding tiny amounts of other elements creates regions that conduct electricity in controlled ways. In lasers, defects can help trap and release energy efficiently. Even color in gemstones often comes from imperfections rather than purity. These controlled flaws alter how electrons move, how light is absorbed, or how energy is stored. The key is precision. Random defects can ruin performance, but carefully introduced ones can enhance it. Engineers and scientists learn how to place imperfections where they are helpful and avoid them where they are harmful. This flips an intuitive idea on its head. Flawlessness is not always the goal. In crystals, usefulness often comes from balance, where order is gently disturbed in specific ways to unlock new behaviors that a perfectly uniform lattice could never provide. Some cutting-edge clocks use trapped ions in crystals for extreme precision. The most precise clocks ever built rely on crystals and carefully controlled particles. In some designs, ions are trapped within crystal-like arrangements and held in place using electromagnetic fields. These ions vibrate or transition between energy states at extremely stable frequencies. By measuring those transitions, scientists can keep time with astonishing accuracy. Such clocks would not drift noticeably even over immense spans of time. The crystal environment helps isolate the ions from outside disturbances, reducing noise that could disrupt timing. Precision at this level matters for navigation systems, fundamental physics experiments, and tests of physical constants. Time becomes something that can be measured with extraordinary confidence. What feels abstract becomes tangible. A crystal holds particles steady enough that time itself can be counted more cleanly than ever before. These clocks show how order at the smallest scales can anchor one of the most fundamental measurements humans rely on. Salt crystals can preserve food by drawing water away from microbes. Salt has preserved food for thousands of years because of how its crystals interact with water. When salt surrounds food, it draws moisture outward through a process driven by concentration differences. Microbes require water to survive and reproduce. By removing available water, Salt creates an environment where many microbes cannot function. The crystal structure of salt allows it to dissolve readily and distribute evenly, maintaining this drying effect over time. This method does not rely on killing organisms directly, but on making survival difficult. The food becomes safer because the conditions no longer support rapid decay. Long before people understood microbes or chemistry, they learned that salt extended freshness. The practice worked because crystal behavior at the molecular level reshaped the environment. Preservation was achieved not through force, but through controlled dehydration. Salt crystals quietly managed water, and in doing so, helped shape human food storage and travel. Ancient civilizations prized crystals for tools, pigments, and early glassmaking. Long before crystals were studied scientifically, they were valued for practical reasons. Quartz was shaped into cutting tools because it fractures predictably into sharp edges. Mineral crystals were ground into pigments for paints and cosmetics. Early glass making relied on crystalline materials like quartz sand and certain fluxes that melted and flowed when heated. These uses were based on observation rather than theory. People learned which stones chipped cleanly, which powders held color, and which materials transformed under heat. Crystals became part of daily life through tools, decoration, and trade. Their value was not mystical at first. It was functional. Over time, symbolic meanings grew around these materials, but their usefulness came first. Crystal properties influenced technology long before they were explained. Ancient crafts were guided by crystal behavior, even without knowing the word crystal. Practical knowledge grew from repeated interaction with ordered matter. Crystals help make fertilizers, releasing nutrients in predictable dissolving patterns. Modern fertilizers often rely on crystalline compounds to deliver nutrients efficiently to plants. The crystal form controls how quickly the material dissolves when exposed to moisture in soil. Slow dissolving crystals release nutrients gradually, feeding plants over time rather than all at once. Faster dissolving forms act quickly but may wash away more easily. By choosing specific crystal structures and sizes, manufacturers can tailor how nutrients become available. This predictability matters for crop growth and environmental protection. Too rapid release can harm plants or pollute waterways. Too slow release can starve crops. Crystal chemistry allows balance. Nutrients are stored in solid form and delivered through controlled dissolution. This shows how crystal behavior reaches beyond laboratories and jewelry into agriculture and food supply. The shape and structure of tiny solids help determine how plants grow, how soils behave, and how efficiently nutrients move through ecosystems shaped by human care. Time crystals are exotic quantum states that repeat in time, not space. Time crystals challenge intuition by showing repeating behavior without repeating structure in space. In these systems, particles cycle through states at regular intervals even without continuous energy input. The repetition happens in time rather than position. This behavior was once thought impossible, but it has been demonstrated in carefully controlled quantum systems. Time crystals do not move like gears. They oscillate in a stable rhythm protected from disruption. The phenomenon reveals new ways matter can organize itself under quantum rules. While practical uses are still being explored, time crystals deepen understanding of how order can exist beyond familiar patterns. They show that symmetry is not limited to shape. It can also govern motion. A system can be structured around repetition in time, expanding what scientists mean by a crystal. This idea stretches classical thinking and opens new directions for studying stability, energy, and order in complex quantum systems. The world's neatest symmetry often hides in crystals, from atoms to mountains. Crystals display symmetry across astonishing scales. At the smallest level, atoms repeat in orderly arrangements that define the crystal lattice. At larger scales, those patterns influence the shapes of individual crystals and even entire geological formations. Mountain ranges, salt flats, and mineral veins often reflect underlying crystal order interacting with environmental forces. Symmetry guides how crystals grow, fracture, and stack together over time. It also shapes how light, heat, and stress move through materials. What feels like decoration is actually a rulebook. Crystals reveal how repetition and balance can scale upward, linking the invisible to the visible. The same principles that arrange atoms can influence landscapes. This continuity is part of what makes crystals so compelling. They act as bridges between scales, showing that order is not confined to the microscopic. Symmetry can echo outward, shaping matter from the smallest building blocks to the largest natural structures we encounter. As our journey comes to a close, you might notice how wide and quiet the world of crystals has become. We've wandered from the smallest arrangements of atoms to towering mountains shaped by symmetry. We've seen how crystals guide light, store memory, mark time, preserve food, and even help us understand the deep rules of nature. All of it built from repetition, patience, and order unfolding slowly, often unseen. Crystals remind us that complexity does not need urgency. That strength can come from structure. That beauty can rise quietly, layer by layer, over time. Whether hidden inside your bones, glowing softly under ultraviolet light, or stretching silently beneath the Earth's surface, crystals are always at work, holding patterns steady while the world moves around them. Now, you don't need to hold on to any of that knowledge. You can let it settle gently, like mineral dust sinking in still water. Allow your breathing to slow. Let your shoulders soften. Let the images blur into calm impressions of light, stone, and time, stretching comfortably wide. If you've enjoyed this peaceful exploration, you're always welcome to support the channel by liking the video, subscribing, or leaving a quiet comment below. It helps these gentle stories find others who may need them. And if you're still awake and curious, another sleepy journey is waiting for you on screen now, ready whenever you are. But if rest is calling, you can answer it without hesitation. Let the rhythms of the night take over. Let thoughts drift and loosen. Nothing more is required of you now. Sleep well and good night.